That's not too terrible a sine wave. All the harmonics are 50 decibels below the fundamental. I'm guessing that the THD is at worst 1%, possibly better. Hi, I'm Kevin. Welcome to my cave. A couple of episodes ago, we were discussing a sine shaper, a circuit that converts a triangle wave into a sine wave. The one we were looking at used a diode ladder, a circuit where the wave is smoothed off progressively by having diodes turn on and shunt more and more current as the voltage rises at the input. We designed one shaper that worked fairly well in simulation, but the component values we came up with were nowhere near the ones that I saw in a textbook example. And I realized that I didn't have an easy way to explain the textbook example. I could simulate the circuit, but didn't feel comfortable about analyzing it on paper, much less designing it. Let's fix that now. The first thing I want to chase is the fact that the circuit in the book uses much smaller resistors in series with the diodes than the one that we designed last time. They're small enough that the last few, at least, are not all that much larger than the ones in the divider chain. They will have a significant effect on what voltage is seen at the output. So let's attack that problem first. How to simplify this resistor ladder? Before we continue, let me interrupt for a few moments. My videos are always free to all comers. Nothing is ever paywalled, and I don't waste your time selling various dodgy products. But I do end every video with a plea that you take care of one another. To this end, all the channel's ad revenue has gone to charity. This month's featured recipient is Médecins Sans Frontières, Doctors Without Borders. MSF is an independent international organization that offers medical humanitarian aid to people based solely on need, without regard to race, religion, gender, or political affiliation. It provides over 10 million consultations annually in more than 70 countries, including some of the regions most torn by violence, neglect, or catastrophe. And it trains health workers and invests in local infrastructure to meet healthcare needs sustainably in a community-driven way. I'm asking my viewers to join me in supporting this organization. This is a small channel, so I've set a modest goal of $500. Those $500 could provide 2 treatments to cure patients of hepatitis C, 4 resuscitators for non-invasive ventilation in newborns, or enough vaccine to immunize nearly 1,400 children against measles during a deadly outbreak. We managed to meet our goal in the last fundraiser, so I'm sure that my wonderful viewers can get us there again. Won't you please join me today? Thank you so very much. What I'm going to claim is that with any given number of diodes conducting, the middle of our circuit looks like an array of 3 resistors. The signal ground at the left-hand end represents some constant voltage, not necessarily a DC ground. Rather than keeping track of that equivalent voltage, what we'll keep track of is the input voltage, the output voltage, and the voltage that was present at the right of the 3 resistor subcircuit when the last diode started conducting. We'll also need their rates of change as the input voltage increases. Thevenin's theorem promises those changes are linear. We'll start the process with the circuit in a state where none of the diodes in the ladder are conducting. In that state, the resistance that we've indicated as Ry will be an open circuit, while the 2 resistances at the bottom will both be shorts. The output voltage will be equal to the input voltage, and the lower voltage will be ground. Our tail represents all the resistors in the divider stack to the right of the point being analyzed. Initially, it's the whole stack. The first step in analyzing the circuit is to split the tail resistance by carving off the next resistor in the stack. That introduces a new node, and it's easy to calculate the voltage of that node. The next step is to add the resistor and the diode that connect to the new node. When the diode begins conducting, it's going to have a constant voltage drop, which looks like a voltage source. The output voltage at the point when the diode starts conducting has to equal the output voltage just before that point. That gives me two simultaneous equations. I'm not going to bore you with the algebra. It's straightforward. It's in the Python code on the project GitHub, link in the video description. I compute the change in the input voltage needed to produce that diode drop, the change in the output voltage that will result, and the ground referenced voltages at the new breakpoint. Now that I know what the next pair of voltages are, we need to compute the next set of slopes. We'll do that by considering only the effect of changes to the input voltage. We'll replace the other two voltage sources with short circuits. The insight that we need is that these four resistors now form a delta configuration. We learned in the last video that every delta circuit has an equivalent Y circuit, and we derived a set of equations for the equivalent resistances. So let's make that transformation. If we combine resistances, we get a 3-resistor sub-circuit that looks just like the one we started with. We can carry out this process for as many stages as we please. And once again, I have a short procedure in Python that does the delta to Y transformation. It also updates the value of the tail resistance in the voltage divider. Finally, we want to update the equations for the rates of change of the output voltage and the lower voltage. That's straightforward. This circuit is now just voltage dividers. The divider equations get another short Python procedure. Then, adding a stage to the circuit is just executing these 3 procedures in sequence. Analyzing the textbook circuit is a matter of creating the initial conditions, adding each stage in turn, and accumulating the voltages. It's easy to plot the circuit response. But it's not right. It's climbing somewhat too rapidly, and it's flat-topping at the peak. What we're stumbling over now is the fact that a diode doesn't really function as a hard switch. Its current increases continuously with the forward voltage drop. In the episode on the Shockley diode law, we measured a bunch of different types of diode and plotted the forward current as a function of the voltage. For a generic small-signal silicon diode, we got a curve looking like this. When we're using a diode as a saturated switch, we usually think of it as a switch that turns on when we reach a voltage threshold, and then a constant voltage drop. What that will give us is a curve with zero current when the voltage is below threshold, and then as much current as needed to clamp the voltage to the diode drop. In the case of this circuit, that's a terrible approximation. One way to improve on it is simply to use a linear approximation. We use a smaller voltage drop, but put a resistor in series with the drop, so the current will increase gradually with applied voltage. It's pretty typical for small-signal diodes to use 550 millivolts instead of 600 for the forward drop, and 33 ohms for the intrinsic resistance. That will give us the curve shown here, and you can see that for forward currents close to a milliampere, it tracks the diode curve pretty closely. It also doesn't complicate the analysis much. We just add the 33 ohms to the shunt resistor for the stage. In fact, I already had that adjustment in the Python code I showed you. The constant R diode in this block is added to the shunt resistor wherever it appears. The result is a lot closer to a sine wave, but now the amplitude is a little off. That's perfectly all right. When I build it, I'm planning to include an op-amp stage to bring the level back to the 10 volts peak-to-peak that's usual in Eurorec. It's trivial to add a trimmer to adjust the makeup gain. A little tweak to the makeup gain, and the fit is darn near perfect. Okay, that's enough to convince me that the textbook circuit really does what it says on the tin. But I still don't feel comfortable that I could design such a beast. The first thing that I want to figure out is how to choose the breakpoints between the line segments. We're going to decide, somewhat arbitrarily, that what we want to optimize is the total harmonic distortion. Please don't start an argument if you're a psychoacoustics person. I know that not all harmonics are created equal. What is this total harmonic distortion? It's the RMS voltage of the harmonics present in the output, divided by the RMS voltage of the fundamental signal. The fundamental signal is the sine wave we're trying to output. We determined last time that if A is the peak output voltage, then the signal has to be A times the sine of the input voltage divided by A. For the slope of the output to be 1 at the origin, the input voltage has to range between ground and A times half pi. RMS, of course, stands for root mean square. That's an abbreviation for the process of taking the value of the function at every point in the cycle, squaring it, computing the mean value of the square across the interval, and taking the square root. If you've had a course in calculus, you might recall that taking the mean value of a function on an interval means integrating it over that interval and dividing by the width of the interval. Taking the square root once again gives us the RMS value. For the fundamental, it gives us a familiar formula for the RMS voltage of a sine wave. What about the harmonics? How do we find them? Well, we're not modeling noise or interference, and all the unwanted effects from this circuit have the same periodicity as the input triangle wave. So anything that isn't the sine wave is some combination of harmonics. If f hat is what our circuit is putting out, then f hat minus f is the harmonic content. We square that quantity, integrate the square over the interval, divide by the interval width to find the mean square, and take the square root to get the RMS harmonic content. This integral is the only part of the overall formula that varies with the resistor values, and the total harmonic distortion varies monotonically with it. So minimizing this integral will minimize the THD. We can compute the integral over each of the individual line segments of the transfer function, and sum the results. That last discussion might have gone a little bit quickly, so let me show what's happening graphically for a single line segment. The desired output voltage will increase as the input voltage increases, and we have the formula for its value. We will approximate that function by a line segment running between two adjacent breakpoints. The formula for that line is simple linear interpolation between the breakpoints. We want to minimize the RMS value of the separation between our line and the ideal curve. It might be easier to visualize if I show the difference as a distance from the axis and expand the vertical scale. It's not this value that we care about directly, but rather its square. So let's graph the square and expand the vertical axis once again. It's the area under this curve that we want. I could do that integral by hand, but I'm far too lazy. Python has a powerful package called SymPy that will do the algebra for me, so let me import it. And I'll define that desired sine wave. This function is intended to work on algebraic symbols rather than numbers, so it's using sympy.sine instead of numpy.sine or math.sine. But I need that sine curve as a function that operates on numbers too. I'll ask SymPy to make it for me. The printed output is not surprising. But now watch what I can do using the symbolic approach. Since I will have the information available, I'm going to have the line segment approximation take the coordinates of the left-hand end of the segment, the interval width, and the slope of the line. I'll let x0 plus h be the abscissa of a point where we're taking the approximation. PWL, for piecewise linear, computes the approximation at one point on one line segment. PWL error computes the difference between PWL's approximation and the desired function. PWL error 2 returns the square of that difference, and int PWL error integrates that square over the boundaries of the interval. All of these are once again working on symbols rather than numbers. But now I'll reduce that integral to a Python procedure that computes it. The formula for the integral is kind of a mess, but I don't care. SymPy has produced an equally unreadable procedure that computes the value of the integral, and that's good enough for me. Now let me move on to placing the breakpoints to minimize that integrated squared error. The idea, of course, is that I'm going to be looking for a quarter cycle of a sine wave, and I get to place a collection of breakpoints, joining them with straight lines to make the approximation. I'm going to be using the optimizer in SciPy to minimize the error. It needs all the constraints on the model parameters to be linear, so we need to be a little clever in how we parameterize this model. What I finally came up with was that we'll have a parameter for the width of each interval and another parameter for the slope of each line segment. It's easy to recover the x and y coordinates by taking cumulative sums. The constraints that we have are that all of the interval widths must be non-negative, the sum of the interval widths must be at most the maximum input voltage, the initial slope must be 1, the slopes must decrease monotonically, and the final slope must be non-negative. With that model in place, it's easy to write code to define the objective of minimizing the error. It's unpacking the parameters, computing the errors using the function that we defined already, and adding them up. Constraining the parameters consists of giving their absolute upper and lower bounds, and giving a matrix inequality for the linear inequalities that we just wrote down. We'll need an initial guess for the widths and the slopes. I will simply do that by placing points along the curve at equally spaced x values. We'll have to force the initial slope to be 1, which will make our initial guess too high, but the optimizer will fix that. After all that setup, a single call to the optimizer hands us back the breakpoints. The SciPy optimizer is hard to use, but only because it's complicated to describe what problem you need to solve. Once you can reduce the problem to an objective function and a set of linear constraints, it does a terrific job. Running the code with 6 breakpoints, we see a theoretical total harmonic distortion of 0.18% or so. Not too shabby for a triangle to sine converter. I have to zoom in quite far before I can see any difference at all between the theoretical curve and the best 6 breakpoint approximation. I can see why HP'd like to design like this. Now, of course, we'll have to convert the breakpoint voltages over to resistors in our ladder. We'll proceed stage by stage, just like last time. The first step is splitting the tail resistance. The equations will be the same, we're just solving for the resistor instead of the output voltage. Next, we add the shunt resistor. Just like before, we're considering only the input voltage, so we can treat the other voltage sources as shorts. We combine the 2 resistors in the middle, and we can recognize that the top part of the circuit is a delta configuration. But this time, we'll also recognize that the bottom of the circuit is a delta configuration, and we'll replace it with the equivalent Y. All the resistor values are known, so the only non-constant resistor will be R sub B. This circuit is now a bunch of voltage dividers. Overall, we know that the desired slope has to equal the divider ratio at the output point. We can solve this equation for the overall resistance of the bridge, and then find R sub B from that. I'm not going to write out all the algebra this time, but of course you can find the answers in the Python code on the project GitHub. It's pretty straightforward in any case. Getting the resistor values is simply a set of successive calls to synthesis find pair. When we take our optimization results and run them through this process, we get the resistor values that are needed for our ladder. Of course, they're oddball numbers. Let's close the loop by choosing the nearest standard 1% values and running our circuit analysis again. The results are surprisingly good. Only 40 parts per million more distortion than with the exact values. I have to scroll way in again before I can see any difference between the theoretical sine curve and what we predict the circuit to do. Of course, all this simulation has to be verified on the bench. But I'm not going to breadboard the circuit that I just designed, because I don't have the precision resistors on hand. Still, I want to get a rough idea of what we might expect from a circuit like this. So I'll try building the shaper as it appears in the textbook. Here it is on the breadboard. Let's give it a try. It looks sort of sine-ish, but even in the waveform display I can see the peaks are sort of sharp. It's not driving the level all the way to where the final pair of diodes are flattening out the signal. Let's try adjusting the trim on the drive level. Oops, that's going the wrong way. Oh yeah, that's getting flatter. Sorry that my hands keep getting in the way. I found that I have to hold the trim pots steady or the screwdriver will pull them right out of the breadboard. Now I've definitely gone too far. The waves are starting to clip at the peaks. Turn it back. I'm close to where I can't do this any better by eyeball. Let me turn on the FFT function of the oscilloscope. Okay, that's not too bad. I can see second and third harmonic peaks. Let's see if I can trim them away. Oops, that's making the third harmonic worse. Let me go the other way. Okay, I've knocked down that third harmonic some, but I just can't get rid of that second harmonic. Back to the drawing board. When I thought about it for a bit, I realized that the resistors of the 2.4 volt reference supplies were probably just mismatched enough to introduce an asymmetry in the wave. So I went back and added a trim pot to one of them, so that I can balance the positive and negative supplies. Let's see if that helps. Once again, I can't really tell what's going on by eyeball without turning on the FFT. I see lots and lots of harmonics, so I obviously need to trim the symmetry. The drive level and symmetry controls interact a little bit, but I can tweak them gradually to a signal that isn't terrible. Off camera, I managed to get it down to where the FFT looks like this. There's a seventh harmonic that's about 50 decibels down from the fundamental, and everything else is really close to the noise floor of the scope. I'd need a proper distortion analyzer to get the performance any better. I could probably improvise something using my AWG and a differential amp, but I'm looking at diminishing returns here. This is surely less than 1% DHD. I'll take it. So we've breadboarded one possibility for a sine shaper that seems to be in the good enough for rock and roll category. I'm going to leave this on the breadboard because I think I'm going to want to come back to it in the future, once we have a few more op-amp circuits under our belts. Coming up, I want to do a few more episodes on the op-amp series, designing, analyzing, building, and testing a few more fundamental circuits. I hope you'll stay tuned for those, and maybe even tell the YouTube algorithm that you wanted to see them. In the meantime, stay safe, stay healthy, stay curious, and take care of one another. Bye.